Hello, it's Rachel. Today we're going to be discussing a topic that's super important for regression, linearity assumptions. It may seem like a super small topic, but it actually is really important when it comes to regression because without these assumptions, you can't really have a good model. This video is part of a series where I take fundamental concepts in statistics and break them down into concise and digestible videos so you can conquer whatever field it is you're using statistics in. Today, we're learning about linearity assumptions. This is Stats in a Few. Okay, so why are assumptions so important? Well, within a regression model, we have this thing called error. Now remember, error is the random variation within our model. It's things that we can't really control. And we don't really know what the true errors are within our sample, so that's why we kind of mimic them off the population error. And the population error is assumed to be normally distributed with a mean of 0 and a constant error variance. And this is important because since we don't know our actual error, we want to assume that our sample error mimics this population error. I know we're assuming a lot of things here, but just bear with me. Okay, so now what are the assumptions? Well, there are going to be 4 of them. There's going to be linearity, independence of errors, normality of errors, and errors that have constant error variance. Now, good acronyms to remember these 4 is LINE, L-I-N-E. L for linearity, I for independence, N for normality, and E for error constant variance. Okay, so now let's go into each of these. So first we have linearity. So the linearity assumption wants to assume that our model is linear. We have a linear relationship between our x and y variable. So it could look something like this, where we have a relationship between our x and our y variable, which is fairly linear and is tight around the regression line. But it shouldn't look something like this, where the data is spread out all over the place. We want our data to be relatively linear. The data could be positive or negative, it doesn't really matter. We just don't want data that's super spread out or that has a curve like something like this. This suggests that we may need to transform our data or use a different model entirely. Okay, now let's do the second assumption. This is independence of errors. See, independence of errors really relies on time-dependent data. These are things like time series data, forecasting, stocks, money, or just any study that has to do with time as a variable itself. Now, regression doesn't really rely on time, so we don't really need to worry about independence of errors. As long as we have a random sample, we can assume that our errors are independent of each other. I'll be making a whole video about time series and its assumptions, and they'll be linked in the description box below once I upload it. Okay, now we have normality of errors. So for normality of errors, we want to make sure that our errors are normally distributed. Now a normal distribution looks like this. And if you remember the 99.7, 95, and 68% rule, we want our errors to be distributed like this. Now in order to actually see this, we want to use a normal quantile plot or a normal probability plot. They both mean the same thing. So with this plot, you're going to see your residuals plotted against the quantiles. Now what you're looking for here is you want to see your residuals along the center line as tight as possible. You don't want to see any major curvature or any straying away from the center line. Again, we want to see that things are linear here. So this plot kind of shows you that the errors are not normally distributed. You can see that there's a major curve going on within the residuals and you don't want that. And if you can't really tell visually if the residuals are distributed normally, you can always look at the p-value for the Anderson-Darling test. So the Anderson-Darling test is the test that basically goes behind the normality assumption. This test has the assumption where the errors are normally distributed. So that would be your null hypothesis. And your alternative hypothesis is that your errors are not normally distributed. So in this case, we want errors that are normally distributed. So we want to fail to reject the null hypothesis. So in order to fail to reject the null hypothesis, we want a high p-value. I have a whole video about p-value that will be linked somewhere around here and in the description box if you want to learn more about p-value. So as long as you have a high p-value, you can know that your errors are normally distributed. Now generally, if your errors are normally distributed, you're going to have a pretty high p-value, something that's greater than 0.5. Okay, the last assumption, errors with constant variance. So remember from before where I said the population has to have a constant error variance? Well, that's where this comes into play. So for this assumption, you're going to be looking at a residual versus fit plot. Now fit just means fitted value or predicted value. It's basically going to take all your predicted values from your scatter plot and plot them against the residuals. And you can see here, this residual plot is basically the linear scatter plot, just shifted a little bit so that the regression line is now horizontal. This just makes it easier to see the residuals. Now what we're looking for here is no significant curving or fanning. We don't want to see fanning because this suggests that there's a pattern between the residuals and we don't want that. So there's one more thing that we need to check after we have all our line assumptions met. We also need to check for outliers. So outliers are any values that stray away from the general trend of the data. Now you'll tell kind of visually if there's an outlier or not. Now outliers get a little bit more complicated, so I'll make a whole video about that that'll be linked in the description box below. But in general, I would just identify any values that stray away from the general trend of the data and mark those as outliers. Okay, so now you did all those assumptions, but what happens if one of them are not met? So in order to proceed with the regression test, you want to make sure that all 4 assumptions are met, as well as there's no significant outliers. If there are outliers, you're going to have to go back to your data and figure some things out. If you haven't met an assumption, you can again go back and do some transformations, or try to see if you can fudge a little bit with your data. But if your model is truly a good model, then all your assumptions should be met, because they're all kind of interrelated to each other. Now, if I'm on a test and I get to an assumption that I'm not sure about, I'll just say proceed with caution, just so I get the points for the regression test in case I didn't validate the assumptions correctly. But just in case, I would just always clarify with your teacher what to do. So that pretty much covers it for this video. I hope you're all clear about what linearity assumptions are and when to use them and how to use them. You should be able to look at a plot and know if an assumption is validated or not. As usual, make sure to comment any videos that you'd like to see in the future and give this a like and subscribe. I'll see you in the next video. Bye!